I did not ask you before. Are you okay with recording the session and posting it online?
Yes, that's fine.
Thanks. So thanks, everyone. Thanks for joining. We're happy to have Julie here. She received her bachelor's in geology from the University of Akron, I think, if I pronounce correctly, her master's in geology from Kate State University, and her PhD from Case Western Reserve University. For 2 years, she worked at Ohio Geological Survey in the energy group on subsurface mapping projects that focused mainly on salt deposits, carbon sequestration, and unconventional resources. She's currently an assistant professor at Stephen F. Austin State University and heads the East Texas Core Repository and the Core Lab. The facility focuses on non-destructive core analysis and correlates data to well-logged data for better subsurface analysis and for natural resources and energy-related issues. She will present to us the potential for rare earth elements in larger evaporitic bodies, examples from North American Phanerozoic salt bodies. So Julie, if you can share your screen and...
It's not letting me. It says it's disabled still.
Sorry?
It says it's disabled. I can't share.
Okay. Just 1 second, sorry.
Okay. No, it's okay.
Yeah, let me try to fix that for you, Julie.
Okay.
So I'll just make you a co-host and see if that works.
Okay.
How about now?
Perfect. Okay.
Thank you. Sorry.
Right.
Sorry
No.
everyone for the technology issues.
All right. I am going to put the chat up. So if people have questions as we're going through, feel free to ask. Otherwise, I'll try to keep an eye on it. It's kind of a lot of information. It's a lot of numbers. A lot of this work is preliminary for everything we've been doing. We had this thought a couple years ago when I was at the Ohio Geo Survey working on one of the salts. It's the Slurry Salina salt, which we'll talk about today, actually. And it just hadn't been revisited since the 70s in detail. So we started looking at it. We started thinking, what other potential trace elements are in here? And so that kind of kicked off this whole thing. And then when I got here to Texas, there's the massive Luann salt. And we started getting samples from Chris Cox down at VP. And so we just it's just been evolving since then. So I'm just gonna give you guys an overview of everything we've been doing and kind of some of the numbers we've been getting looking at these for rare earth elements and other potential for critical minerals. Okay, there we go. So what exactly is a critical mineral? A critical mineral is anything, it's a material that's been deemed by USGS as being essential and necessary to our economy. They call them minerals, but a lot of times when you start looking at the list, they're elements. But we as geologists know that these are in mineral form, right? A lot of times we're not going to get pure lithium. It usually comes as an oxide or it's bound to calcium, just other things like that. So what also makes these critical is that the supply chain has been deemed vulnerable to disruption. This could be either a political issue, this could be scarcity, but either way, we are not, at least here in the US, we don't have primary sources of these, or at least that we know of. So again, mineral form, but looking for certain elements in particular to use, and then we can extract those for use. So when we look at the USGS table of critical elements. There are now 55 elements that they have put on this list. This was updated in 2021. Previously in 2018, 2017, there was 35. But with our continued use or continued transition towards renewable energy, they've been seeing that we need other ones in here too. We need to start looking for potential domestic sources. Some of these, so anything boxed in purple is what the USGS has mentioned as being a critical mineral element. And some of these might seem odd, so like carbon, but really what they need is graphite. They need that specific form for lubricants and other resources. When we start looking at potassium, it's really for fertilizer and things like that. And then other ones of these, like the rare earth elements, those are very obvious. We need those for batteries. We need these for generators. We need a lot of this for the renewable transition. So what exactly are they used for? This was a report done by the IEA in 2021. This report specifically was looking for critical minerals for clean energy technologies. As we were starting to push towards this a more diversified energy portfolio is a good way of putting it, we are going to need resources for that too. So we might not need oil and gas or other fossil fuels. However, making a battery does require tools. It requires materials for it too. So looking through, so on this chart, anything that's orange is high, anything that's red's high, orange is moderate, and then blue is low. We don't really use it. So when we're looking at solar panels, we're actually using a lot of copper when we're making these, and we're using a lot of aluminum. And they don't mention in this report, but silica is also used in these solar panels. So we need these resources in order to make them. When we're looking at wind, we need copper, we need nickel, we need rare earth elements, chromium, zinc, and aluminum in order for wind to actually function. Even still, when we start looking at nuclear, there's copper, nickel, chromium that are going into this power plant in order to make this function. So even though these are renewable resources, as in they aren't using fossil fuels that are being consumed, however, they still require materials on the front end. So what else are they used for? Copper and aluminum are also used for transmission lines. So even if we don't go towards this renewable energy transmission, we still need this in order to function as a society. Neodymium is used in magnets, it's used in lights, batteries and alloys. We use it for glass polishing and ceramics, and then it's also used in catalysts for our cars. Scandium is used in TVs and also in fluorescent lights. And then PM is used in watches and pacemakers. So potassium, again, we're using this for potash or fertilizer. So even though there's this push for these renewable resources and finding these critical elements for those, they're actually an integral part of our everyday lives. So the supply chains for select minerals needed for clean technologies. There are specific locations we get these, and this is why they could potentially be deemed as a vulnerable supply chain. So if we look on the downside, if we look at the mining and processing end, a lot of this is actually coming from China and it's Congo, Dominican Republic of Congo, Chile. There are places where we have, in the US at least, have great relations with, such as Australia, but our political relationships with China are obviously very, they go back and forth, right? So, but if we look at where all the mining and processing comes from versus who's using them, the US and the European Union use a lot, but we don't produce a lot. So where else could we potentially find these resources? So the search for REEs and other critical elements, typically when we do this, it's mining, it's hard rock mining. And so this can be potentially very disruptive to the environment. A lot of times this is strip mining. It can be dangerous. And even still, when we're doing this, we're still looking for, particularly on the rare earth elements percentage, like less in percentages. We're looking for ppm, hundreds to thousands of ppm. Some of the other metals, so iron, when we are looking for iron, we do look for higher concentrations, so particularly up to like 50% plus of iron in there. But for some of these other ones, these critical elements, the percentage needed to be economical is actually quite low. Right now, we're also looking at shales. So shales have the potential to have enough metals in them, so such as nickel, copper, etc., to actually be a viable resource. Particularly with all the fracking and all these unconventional resources, we could take something that is a waste product and repurpose it. There's also people looking at brines. So there is enough lithium in the Smackover for it to be commercial. And so I have students coming up, like past students, and they're like, I'm getting somebody asking me for my brine from the Smackover wells we're drilling. And I'm like, yeah, they're looking for lithium, and it just, everything starts connecting. They're like, that makes sense. So this is naturally occurring lithium in the Smackover. If I remember correctly, it's bonded to the calcium ion. And so they can easily produce enough lithium out of these brines, which is, again, a waste product from these oil fields. And then another place they've been looking is coal. So the 2017 DOE report was looking at underclays and other parts of the coal bodies for rare earth elements and critical minerals. A lot of these are concentrating in very similar fashions, either in these sulfidic and oxic environments where everything just kind of starts concentrating down, or it's just occurring in the brines as they're starting to pass through, or they're occurring in the ancient seawaters and everything's just starting to concentrate in. So another potential source is seawater, right? A while ago, not that long ago, but they were looking for lithium in seawater. Could we produce enough lithium or gold or any of these other ones out of seawater, because it's in there, but it's in very, very low concentrations. So these down in here, although it looks like 0, these are actually part PPT, PPB concentrations. These are very small concentrations. And so we know it's in there. It's just not high enough concentrations to be economic yet. So if we find them in seawater, what about evaporites then? What about a product that's already being naturally concentrating that seawater or those brines? So would they concentrate in evaporites? And the short answer is yes. So a modern analog for everything that we're doing is Sears Lake in California. So it's located right in here. It's part of Death Valley. Here's the Sierra Nevadas. Right in here, so it's an endorheic lake. It's arid. It does get a little bit of recharge. And so it has some subsurface recharge that comes in. It's currently exploded for salt, borax, gypsum. There's a lot of surface mining that goes. They can strip it straight from the lake. It's beautiful. Some of these resources that they get, I'll show you a picture of some of the salt that's actually being taken from here. And so it's just a naturally occurring concentration pool. So we have these brines. They are isolated. They get some recharge, but not enough. And so as they are naturally concentrating down just from sunlight, they are producing some of these, they are producing evaporites. They are also concentrating some of their REEs. So the solutes in this system are being sourced from the Sierra Nevadas, and there's also hydrothermal springs underneath. So when we look at them, and when we start measuring what's in them, these are known to have rare earth elements being concentrated in them. So this right here are salt hopper crystals that were taken from Sears Lake. So we ran through and we're like, what's in it? I know it's salt, but what else is in it? We tested just using a handheld XRF, and we'll talk about the methods some more later. We tested the pink copper crystals. We tested the dark pink ground mass. And then on the underside, if you would flip it over, it's a light pink ground mass also. And so we just ran it. And so obviously we have chlorine, right? This is a salt. We do have a little bit of sulfur, which is coming in. It's probably in hydrite or some other form, gypsum perhaps. Little bit of potassium. But when we start looking at the trace elements, what we find is in the underside pink ground mass, we actually have about 2,500 ppm of vanadium. We're actually finding increased amounts of titanium, and that could potentially be coming in from some of the siliciclastics coming straight off the mountains. We have a little bit of barium, and we actually have some increased levels of uranium. And so this is actually an interesting point. So it's probably being concentrated again from the ground, from the seawater in the area. But there's two potential reasons that we could be having this pink color. So some of it might be biological, because this is a active system. This is a modern salt crystal. When I got this salt crystal, it smelled like shrimp. You can still smell the organics on it. It's either from that, or it could potentially be from the uranium too. It might not be decayed enough, but in other salt crystals that we find in other systems, they don't actually have potassium making them pink. Their levels of potassium are so low. But one thought is that it might be the uranium. As it's decaying, it's starting to damage some of the crystals. But as we start looking at the rare earth elements, we are actually finding increased levels of REEs. So neodymium, praseodymium, cerium, lanthanum, we can find anywhere from potentially about 175. Some here is low, there's not any, but with neodymium, we're getting levels up to 800 ppm. So these could be significant quantities of these resources. So our modern analog has shown that we do have an enrichment of other trace elements, not just these bulk elements. It's not pure salt. So are there other critical elements or minerals in other evaporitic bodies, and ancient ones too? Because Sears Lake's not going to be enough to create a robust economy from this. So we have a combination of cores and cuttings from 4 different locations across the United States. These are located in the core repository here on campus. And so this one came from Ohio. So this is from the Ohio Geological Survey, although I have it here. And the rest of these we have here on campus. We have the Salina group from Lake County, Ohio, which is up in here. We have the Permian Hutchinson salt from Reno County in Kansas. We have the Permian Salado salt from Pecos County in Texas. And then we have the Jurassic Luan salt, and this is from an offshore well. When we went through and did this, we used a handheld XRF. It's a thermal nighttime XL3T Gold Plus. And so depending on the sample, if they were hand samples or if they were cuttings, we would crush, sieve, pack, and pack them into a holder. If they were slab face, if they were slabbed, if they were core, if they were slabbed. And so we would clean the core and then we would run it directly on there. Just to verify that what we were finding was correct, we would take a little piece of the core, run it once before crushing it, and then we would crush it, sieve it, and pack it into a holder also. Each one of these we would run for about 5 minutes. We can get elemental compositions technically from magnesium through uranium. Some of these we don't have the concentrations are. However, some of these we don't have the calibrations for, but really what we need, because we get 40 different elements, we focus on the bulk elements, the critical minerals, and we're going to focus on the rare earth elements, particularly down in here. We then went through, and some of these we did run on XRD, just kind of verify some of the other minerals that we're finding in here. And then we also ran SEM, and that's really to focus on crystal structure, because this way we can kind of start getting an idea if they're primary or secondary. Have they underwent diagenesis? Have they been dissolved and reprecipitated? So let's start with the Permian Hutchinson salt in Kansas. This is a halite interbedded with gray black shale. It's bedded gypsum and anhydrite throughout. There are some conflicting studies on whether this is marine or continental. And so it was during this time that we were starting to, the seas are starting to regress. So right in here is where we're located. So this is currently being used. It's a shallow brine pool for wildlife. It has been used for well beyond since we've been here as a society by Native Americans also. Currently, it's being mined at the Hutchinson Salt Company. It's about 645 feet or 190 meters below the surface. It's not terribly deep. It can get up to 99 meters thick. It's used for road salt, feedstock for animals, and it's also used for oil well mud to adjust to alkalinity. So when we start looking at these are hand samples. We would take chunks of them. These are taken directly from the mine. We would crush them, sieve them, and pack them, and we run them on the XRF. So what we're finding is that we have increased levels of chlorine. We do have some sulfur, potassium, and some calcium. And that kind of makes sense based upon the lithologies that are known in this section. However, when we start looking at some of the trace elements, we are finding some magnesium. We're actually finding some barium in here, which is interesting. This isn't a contamination. Some of these will have barium contamination due to barite from the drilling fluid, but this isn't an active mine, so there's no drilling going on. But we actually have really high levels of strontium in the red salt right in here, up to 7,000 ppm. When we start looking at the rare earth elements, and I'm going to focus more on the REEs because these do not need as high of concentration compared to some of the other metals. Neodymium, we have upwards of almost 600 ppm in. Praseodymium, cesium, and lanthanum. These are also decreasing. However, we're stuck at hundreds of ppm of all of these. So I'm actually going to put up, I have the wrong chat. Okay. So the Permian Salado salt. So we're in the same time period. We're just going to move to a different section of the United States. So at this point, we have withdrawal of the inland seas that covered much of the region during the Pennsylvanian. The two are starting to come together. And so what we have is closing of this ocean in here. It is hot, it's arid, it's abundant, and there's abundant tidal flats. There's red beds throughout. So you have this combination of these muddy areas, and then you have this salt coming in and precipitating too. Can the Hutchinson salt be here? Let me move back a little bit too. So can the Hutchinson salt be tested for paleontology, the shales and organic rich, to determine if there's any marine influence? I don't know that. So one thing I do know is that you can look at the textures of them also. And I was reading something yesterday, so I would have to read more about it. And you can get an idea from the textures and probably some of the inclusions in there too, particularly the strontium inclusions, now that I'm talking out loud through this, and the bromine inclusions, and you can get an idea of freshwater versus marine influence in there. I don't think it's just been studied enough. When I start going, so a lot of times, and this is the problem when we were working at the Ohio Geo Survey, they just use it for salt. Like they test how much non-dissolvables are in there, so how much anhydrite and clays, and that's how they rank the purity of them. And so they just do those basic tests. They're not looking at anything else, and that's it, right? Because salt's relatively cheap. So there's not been a lot of studies, generally speaking, on any of these. The Luan is more studied for like structure. So the Permian Salado salt. Again, we're just moving a little further south and to the west, but it's the same time period. When we're looking through the Permian Salado salt, we have cores on this one. We don't have an entire section, but we do have about 50, 60 feet of core. And so this is on the Central Basin platform going into the Delaware Basin. And so this is bedded potassium bearing salts, and I would call it potassium bearing salts versus sylvite because the potassium level, it's not a pure sylvite. There are clays throughout. You also have organic inclusions throughout. So it's interesting. In the other one, there's not as much, at least in the hand samples, but in this one you can see more organic inclusion. So that would be a really interesting study to also add into these stories. The other interesting part about the Salado salt is that you can get meter to centimeter scale cycles of these anhydrite, polyhalite, halite, fine grain siliciclastics. You just get this constant cyclicity to it. And so you can actually see when we have addition of water into the area, into the basin, and then restriction. You get this constant climate cycles. Essentially, you could think of it as climate, or you could think of it as tectonic, and I'm not sure which one it would be. It's probably, I would imagine it would have more of a tectonic influence at this point. I don't know. I'm thinking about that out loud as we're talking. So this can get upwards of almost 400 meters thick. It's about 700 meters below the surface. It's not that deep. And so what we get are these cycles. So right here is a couple boxes of the Salado salt that we have. So you have areas where you do have a little bit more clear. I do have some sections that are like crystal clear. And then you have a lot of this is actually clay inclusions being included in here, or organics. And so here we are. We're here in West Texas. So earlier we were here, now we're down in here. So when we start looking at this, we can go through and we initially run the bulk element, or we start looking at the bulk elements. So we can get an idea of some of the lithologies going down. And so the silicone and calcium are the siliciclastic component. So as we start coming through here, we can start getting these increases and decreases of essentially clay minerals coming in. Our chlorines obviously are halite, and then our sulfur is our sulfate. And so as we start coming through, we have a little bit of cyclicity to here. The boxes that we have, I don't see any distinct beds of anything but the halite. And so at the tops and bottoms, we do have clays, we do have shales, but I don't see anything particularly in this one. You might have to get to a mine, or if they have more complete section of here. But overall, what we see is salt with clay and silt inclusions. In this, so I was asked, do you see different concentrations in fracture fills? Not in the Salado, however, I didn't test it particularly. So the ones that I have fracture fills on are the Salina group, which we'll talk about here next. And so I don't know that one. I don't think I concentrated on that, but we'll talk about that. So when we start looking through this, we have right in here is our salt. And so what we're seeing is this interbedded of the silicone as we're coming through. And we can kind of see that in here. We have this, essentially, you can kind of go by color, where we have these darker sections, we're having more clays and coming in versus the lighter ones where we're more pure salt. So when we're looking at the trace elements, some of these are consistent going down section. So up in here is actually our clay. This is the shales. I didn't measure the bottom shales in here, and this is our salt section right in here. So our barium actually changes throughout. It has distinct horizons as opposed to being, a constant line throughout. Our manganese, however, is at a fairly constant 300 ppm. Some of this might be either increases in clay content, which I actually have the silicone that we can pop up here in a moment. So it just might be concentrating in the salts. However, we have some other bases coming in and kind of compensating, I guess, for some of that. Chromium has a couple distinct spikes, and I don't have an exact answer on why, but here we are. Strontium, so strontium's often, the isotopes are oftentimes used for, to determine freshwater versus marine water influence, but those are, again, isotope levels, but we are having various amounts as we're coming through. Same with zirconium, which is probably correlating a little bit more to the clay content. Zirconium tends to be correlating to clays in a lot of these. And then finally, cobalt. I'm not sure the economic concentrations that you need for cobalt to be mineable, but we are sitting around probably about 90 ppm. And so when we're looking through our salt section, again, what we have is this it's not consistent throughout. What we're having is a change going through. And some of this could be dissolution and reprecipitation. Some of this could also be, if we start bringing in our siliciclastic component, there is a little bit of correlation, particularly as you can see with the strontium, on how these are coming through. So there are different bases that are concentrating some of the elements that could potentially be of interest. So finally, looking at the REEs, what's interesting is the lanthanum, praseodymium, and eudymium, they actually correlate very well with each other. The CE and TE, they kind of, and I know TE is technically not an REE, but it is a rare element. So I do stick it in this throughout. And the CE and TE actually correlate quite well together too. Cesium and tellurium, actually, a lot of times they're found together also when I was doing a literature search. So coming through, some of these we have upwards of 1,000 ppm of eudymium coming through this section, which is actually a significant potential resource for these. Again, looking through these, it's kind of interesting to note how some of these are very consistent throughout, even though we have increased siliciclastic or organic content in here. So some of the small scale fluctuations could be that coming in, kind of diluting down the system. But overall, what we're finding is some of these are pretty consistent throughout as we're coming through. I don't have an answer as to why the CES and TE are variable in there, but that's something we need to figure out. There's a couple things we still need to figure out. So looking at averages, we're at about 390 for lanthanum, 645 for praseodymium, 24, it's pretty low, but we have a lot of zeros in there too, for cesium, 65 for tellurium, but we're at about 1,000 ppm average for neodymium, which is significant. So again, lanthanum, praseodymium, and neodymium correlate, cesium and tellurium correlate, and you'll see this pattern actually consistent throughout. So moving on to the Jurassic Luan salt, this is a massive salt body that's found throughout the Gulf of Mexico basin. It was deposited during rifting, restriction, and intermittent pounding throughout the area. It's known from Mexico all the way over to Florida. The other interesting part about this one, it's up to 4 kilometers thick. So it's massive. It is one of the primary, I would call it in my head, at least, it is a driving mechanism for a lot of the offshore oil basins, actually onshore too. It's part of the entire Gulf of Mexico petroleum system. It was deposited during subtropical and arid climates. It's halite with silty, sandy halite intervals, impure halite intervals, but overall it's a pretty massive salt body. So this one was cuttings. So we went through, we would, they were cleaned before we got them. However, some of these I think are probably contaminations from the drilling fluid. Because we're dealing with cuttings, I didn't want to rinse them too much and dissolve off everything, dissolve off the entire sample because they are pretty small. So we need to go through and kind of verify a couple of things and run a couple more tests. But we were able, so these were sampled every 90 feet, so about every 30 meters going through the section. This is actually my depth plot is gone, but this is in feet going down through, not meters. So we could do something very similar. So when we're looking at our silicone and our magnesium, those are going to represent our siliciclastic component. Our chlorine is going to represent our halite component. Our sulfur in here is anhydrite, and our calcium is a little bit complicated. So normally if we have sulfur and calcium correlating very closely, that's your sulfate component. However, when we start looking at the calcium concentrations, we see that we do have, but we have a little bit of, we have negative correlations, and we have a little bit with our magnesium too kind of coming through. So using it purely just based upon, you know, if I have sulfur and calcium, it's sulfate. It's, the mineral model for this would need to be modified a little bit. So coming through, no. So I was asked by Kathleen, were you able to distinguish between elements in salt matrix versus trapped as solid inclusions versus dissolved and fluid inclusions? So when we run this, the XRF, it has a spot size of about 3 millimeters, and it's going to measure whatever's underneath it. And so going through, we would, particularly when we were crushing, we would try to either get pure halite samples. So like I would, if you go back to the Hutchinson, I made sure to get just white salt, like clear salt. I would get ones with organic inclusions, or I would try to pick out as much so we could hand pick it out. But we weren't able to, like the XRF is unable to distinguish that. So that would probably be more if we did like a EDS or looking at it with microprobe. We would be able to actually like get a much smaller sample size and be able to pinpoint a little bit better what's doing what. And so, okay, sorry, moving on. So when we go through, we can distinguish different boundaries with the Luan. So this study actually was because Chris, she saw that we were interested in salt, and for BP and other offshore operators, the Luan is such a mobile formation. And a lot of times we have multiple salt bodies colliding, and they create these suture zones. And they need to know the mineralogy of those suture zones. So if they drill through them, they could adjust their drilling fluids so it doesn't become a disaster, particularly in offshore. And so that's what we're doing. Like, can you figure out the suture zone? Can you tell me what's in the suture zone? And it's like, of course. And that's what we did. And it's actually some really cool results. So coming through, so we have the overlying formations, we have our salt body. We actually have something in here that has siliciclastics being incorporated into it, pretty pure salt. I'm pointing at my screen that you guys can see what I'm looking at. And then underneath we have, it's another shaly body, salt. So really what we get is it's overlying Pliocene Miocene formation. We have the Luwian salt coming through, and then we have underlying Miocene formation in here. Right in here is actually our suture zone, what they call a suture zone. It is where we have two salt bodies colliding. So what we have in here, it's quartz, mica, and other clays and hematite, and it's coated on salt. And so just having this mineralogy for them as they're drilling through this section, they can then figure out what they need to do. So when we're coming through, I have an extra, I didn't put all my animations in there properly, but so we can come through and we can look at the trace elements also. We can divide it up using our same lithologies that we just did on using the bulk. So we will see a couple differences between this and some of the other ones. That barium probably is contamination. We need to go through and we need to get the drilling fluid composition, but then we can run a couple tests where we can kind of lightly dissolve off some of any coatings that's remaining on there and just see if we can reduce that concentration. If we pretty much dissolve off a good chunk of the salt and then we still see a lot of barium, it could be naturally occurring then. The chromium is probably contamination from the drill bit coming through, particularly because it doesn't seem to really correlate with anything. It's just these very discrete spikes. We do have upwards of 1,000 ppm of magnesium, a little bit over, but they seem to be concentrated a little bit more towards these shale lithologies. Same thing with the zirconium. They're concentrated in the shale lithologies. We also see spikes in the suture zone, which has clay minerals and other things incorporated into it. And again, with the cobalt, so it's interesting on the last set of salt, we did have like very discrete cobalt spikes in here, and we do have some cobalt coming in here too. I'm unsure on what that means, like with regard to depositional history or anything like that. Those are still some of the questions we're trying to figure out. Looking at the REEs, we have, again, very similar patterns, although concentrations are different. So let's divide them up and we can kind of look at them again. So the lanthanum, praseodymium, and neodymium, again, all correlate very closely. Concentrations are different. Concentrations are lower compared to the other salt body. And then again, cesium, tellurium, and scandium, scandium actually has nothing in it. And very rarely do we see anything in the salt bodies, but cesium and tellurium do correlate. And they have these discrete spikes. And so when we're looking at the overall concentrations, we have about 100 ppm of lanthanum, 112 of praseodymium, 8 ppm of cesium, 23 of tellurium, again, because we have very discrete horizons. There's a lot of lower than detection limits in there. And the neodymium is upwards around, it's averaging around 214. So we are finding these concentrations in this salt body too. And so, okay. And I don't have anything more than that. I'm still working on depositional modeling, how they're getting in here and kind of what we're seeing. So looking at the Silurian Salina group, this is moving up towards Ohio. So this is going north and over towards the east and also back in time a little further. So this was during the Silurian. It's deposited in Sabkha to Salina to subsea conditions. As you go into the basins, getting deeper and deeper, and we are concentrating and getting these. The core that we have is in Sabkha to Salina conditions, and you can tell, and we're going to look through the cores until you can see them. There's this constant opening and closing of the Appalachian Basin in here. So here we are. We have, we just got done with the Taconian orogeny previously. We're starting to go into the salinic disturbance. And so right in here is the Appalachians. This picture doesn't show it well, but there are, there's going to be like reef mound buildups, and there's also an arch right in here. And so with sea levels are constantly regressing and it's restricting, and then we have sea levels coming back in. And so it's this constant back and forth. And so this is a very cyclical formation, particularly compared to the Luann, which is just almost pure salt going down through. And then there's connections to the Michigan Basin up in here. So sometimes it's totally open and sometimes it closes and we just back and forth. So again, we're coming into Ohio right up in here. So previously we were here, here, and now we're coming up to the northeast. There are multiple salt beds interbedded with dolostone and hydrite, shale, and siltstone. This is the set of rocks that actually kicked off this entire thing. So we do have more core studies that are being done with this, and we're going to go into the cores a little bit more in detail compared to some of the other ones. Again, it's very cyclical in nature to deposition. Overall, it's about 1.5 million years of deposition. So the Salina is divided from the A through the G going up section. We use a lot of well logs to actually map out this formation in the subsurface. So right in here, there's actually a little bit of an anhydrite coming through, and then we start having carbonates. And then as we start coming through, we have this back and forth between anhydrites and carbonates and some shales in there. The sea actually does have a salt in it that it's very difficult to distinguish on a well log. So I had that question about fracture infills. We're going to look a little bit at that. I don't have an answer to you exactly, but that's a good point. But I do have a picture of the fracture infills. It is a red, highly radioactive salt. It looks like a shale on the log when we're looking at well logs due to that uranium that's being incorporated in it. Originally we thought it was potassium. We ran ICP-MS on it. It was uranium. We were a little bit put off by that. It's just kind of like a little bit mind-blowing because we had to stop and think about why. But we can see it. There's beds of red salt in here, but it's very hard to distinguish on here without using some of the other parameters. So we have anything that's highlighted are salts right in here. So we just have this constant back and forth. We eventually get to a section in the F salt where we do have massive beds in there. And these ones in the F and some in the E, when they do thicken up, these are mined. So the F is currently subsurface mined underneath Lake Erie. So right in here, just a little bit to the west of where this core was for road salt. And then the E is actually brined a little bit further down right in here for table salt by Morton Salt. And so this was actually a mapping project to revisit the history to see how much salt was actually underneath our feet. But then also we wanted to add in the trace element. We want to do a little bit of geochem on it too. And so I'm just going to do the geochem today. So this is a combination XRF, XRD, SEM. We also wanted to reevaluate the depositional environment because originally when it was published in the 70s, it was thought to be purely deep water, a deep water system, kind of like the Luann. When we start looking at the core, there's a lot of discrepancies. So I think it's a very much a mixed system. So I'm giving away all the final answers. But okay, so when we look at the Salina group and core, it's halite and a couple other lithologies. This is coarsely crystalline. This one has organic conclusions throughout. It ranges in color. We can see everything from yellow to clear. We have these grays, and this is going to be organic conclusions. And then we have this lovely red right in here. Right in here is one of those fills as it's coming through. Again, I don't have an answer on your question. So, but that would be something interesting to look at. We have dendritic shales coming through. We do have back beds and fracture fills coming through. Some of this has been remobilized, but nowhere near as the Luann. I'll show you some pictures later on, and you can see some of the folds in here as it's being moved. Some of it's been dissolved and precipitated too. When we look at it in SEM, and so, oh, this is such a good question. This is just perfect timing. Kathleen just asked, there's a publication about chevrons in the Salina, which suggests shallow surface brines. That's exactly what we have. We have chevrons in the SEM. It's beautiful. I saw this and I was like, oh my goodness, it's amazing. That suggests the shallow subsurface, but also primary precipitation. And so you can see right in here, you can just imagine these are like an edge of a salt crystal, and it's just salt crystal, just like going back through. I would love that paper, and I'll look it up if I can't, if we don't have a chance to connect afterwards. So we also see when we're looking at other salt bodies, so these are two different samples. And so we have salt precipitated, thank you, and fractures and pores throughout. And so this is actually kind of contradictory. It is telling us that this is primary, this is probably secondary. This is coming in afterwards. This is also what they call a mosaic pattern, and it's thought to be secondary also. Okay. Oh, fracture fill. You can see the perfect, almost perfect little cube and how they're kind of growing into each other in here. Same with this. You can see it kind of growing in there. So also looking through here, this is a very different system compared to the other ones. We do have anhydrites. These are dark gray to black. They are massive. They are hard. I don't like dealing with them because I can't crush them. So the salts are easy to crush, the anhydrites are not. And the interesting part is, particularly because originally this was thought to be a deep water setting with no life, a totally barren landscape. We find fossils. We do find occasional fossils coming in. And then we also find those organic inclusions too. And then I'm gonna show you the dolomites here. I'm giving it away that we also find algal mats. So there's something, it's dynamic. There's a lot going on. So looking at the duller stones, these can be buff to gray. We have anhydrite growth actually coming in. So what we have as, so this is actually an algal lamination in here. These have algal textures to them, but then these must have been drying out, and so some of this sulfur rich water was then able to precipitate out anhydrites also, but then we get more we get more algal mats, and so it's this constant back and forth. These are the algal laminations, and then we do still have some mud cracks coming in. This entire section, this one is brown because it's oil stained in here, so it's producing, actually there's enough organics. I don't know, and I guess we would have to do a little bit more geochemistry to actually figure out where the oil is being sourced from. I'm trying to think if it's going to be primary, like if it's self-sourcing or if it's coming from elsewhere. But because there are other areas when you go into the Michigan basin, these reefs are producing oil out of them. So we also have so there's some more anhydrite growths coming in. This is not in the algal mats, but we have some of these muds, and then we have anhydrites being produced out of them too. We also have pyrite inclusions in the middle of these anhydrites. So that's an interesting fact that's coming. We have in this anoxic sulfidic rich environment that's able to produce these anhydrites also, or these pyrites also. And then some of these are partially dolotomized. So we have a mixed signal on the calcium magnesium correlation, and sometimes we'll have higher levels of calcium compared to magnesium. They're not fully dolotomized throughout the section. And so when we look at the anhydrite growth going down core, you can see that's what this black is right in here. This is what it looks like on a larger scale. Looking at, so it's the texture. That's how we're recognizing them in this system, is going to be the texture. So when we're looking through at this, how we have all this stratification in here, that's our algal mats. And I have someone on campus that's an expert in carbonates. And so he's the one that I'm like, Kevin, is this an algal mat? He's like, yeah, it's an algal mat. And he told me all about it. I'm like, okay, cool. Thank you. So overall, what we're seeing in these cores is a cycle of deposition due to evaporation and siliciclastic influx. So we just have this constant back and forth. We have this recharge coming in so we can continue on this cycle. This is, again, a very different system compared to the other ones. And so looking through, so this one, I had hand samples. So some of this I had core and hand samples. So we actually went through and we sub-sampled the core, and we crushed, sieved and packed, and ran them on the XRF. And so again, when we're doing core versus hand, versus the crushed, sieved, and packed samples, the core is gonna be a little bit more heterogeneous. Like when I crush, sieve, and pack them, I'm homogenizing the whole section. So I I will dig through my computer when we're done and I will see if I have one. I'm pretty sure we did. So let me see, because I have a lot of them. Don't let me forget. Okay, so we see a lot of similarities. The thing is, when we crush it and pack, it's homogenizing a little bit versus if we're going down core, we can like hand pick certain ones. I also don't like destroying core, so I try to leave it as is when possible. So but with some of the samples, if they already subsampled and the Salina salt was subsampled in that section because it was previously run for other things like back in the 50s and 60s, you need a certain thickness to it so the sample is not being shot through. And so you just need a certain density. And so we can make sure we have that when we crush them and pack them. So again, okay, so list of classic components are silicone. We can have chlorine is our halite. Our combination of sulfur and calcium is our anhydrite. However, you will see changes going down. So like right in here, we have low calcium, and then we have other places where we have high calcium right in here. This right here is corresponding to our magnesium. So calcium kind of plays two roles, actually, just kind of looking. And then our magnesium is our duller stone. And so again, going back a couple slides, this is cyclic. So we go from the A through the G, and we can actually figure this out. And so in this sample, we don't have the A section, but we have the B. We can go through anhydrite. We have the red sea salt. So those beautiful red cores that we saw in there, shale, D, anhydrite, and we just keep going up through. And then we actually have some of the overlying formation right in here. So we can just get a generalized lithology going down through. Yeah, so looking at the trace elements, we can do something similar. So let's put it on our lithology so we can kind of keep track of where we're at. And so we have various amounts of barium, magnesium, chromium, strontium, zirconium, and cobalt. And the one thing you will notice is how variable it is. And again, we have a lot of lithology changes in this core too. When we start looking at trying to figure out where things are happening, because at first I was like, we're gonna have all these critical elements and these salts, it's gonna be fabulous. And then after this core, I realized that it's concentrating in a lot of different things. It's not exclusive to salt. So when we're looking at the strontium, it actually has a really good correlation with the sulfur. Besides a few points, I mean, that is a beautiful correlation for geologic materials. That's going to be the celestite right in there. We could do zirconium. This is associated with the shales. That's a pretty good correlation. And that is a known thing to happen. A lot of the zirconium is going to be used as an indicator in these shales for various systems, whether it's, and I can't remember offhand if it's anoxia. There's a couple depositional settings that it can be used for. So some critical elements are found in the chloride or in the chlorine, so associated with salt. But however, we actually find more in other bodies. We're finding more in the anhydrites in the shales, actually. So, but you got to realize a lot of these are being precipitated or sourced in a very similar setting. So this is all kind of coming. So any of the evaporites, particularly, they're all coming from the same seawater. So it kind of makes sense that any of the anhydrites, carbonates, or salts are going to have these in there. And so one question I've gotten is, what's the solubility? When is it coming out? Is it just going to precipitate out first, or is it going to precipitate out later? And then if you do that, if you can figure that out, you can then start predicting kind of where we would find these. And I don't have an answer on that either. I'm just talking again. I talk a lot. I can do this all day. So looking at the REEs, we are variable down core again. And let's put up our lithology so we can keep following along. We have very similar correlations, how they correlate with each other. They are abundant in the halite, but also other lithologies. So instead of going piece by piece going through, let's just kind of look at some cross plots. So when we're looking at the chlorine, what we have, when we have high levels of chlorine, we have upwards of about 700 ppm of neodymium, and they kind of decrease coming down through, but we can get up to 700 ppm of these rare earth elements. Looking in the other bodies, particularly the anhydrite, we can get upwards of about 1300 ppm of these. So they are concentrating in the salt bodies. However, they are concentrating more so in some of the other bodies. When we're looking at the sulfur, so we're looking at the anhydrites, we actually are seeing increased levels in a lot of these compared to the salts. So it's not just the salts, it's all the evaporate systems. So that's something we need to figure out. So coming down through, we can look at some of the averages. The lanthanum is about 164. Looking at the praseodymium, 248. Cesium, we don't really have that much. We have very discrete spikes upwards. We have an average of 13, but we can get upwards of 50. Again, that average is more so because of the zeros. Kind of you can think of them as outliers. So potentially mode would be a better way to represent some of this. Tellurium is 41. Neodymium is sitting around 390. And then when we're looking, so these averages are just for the salt bodies. I'm sorry. We don't really have anything in scandium. There are a couple sections, but we're not really getting much. And so, okay, overall, I've told you a lot. It's 9 o'clock, I can talk a lot, I'm really sorry. So overall, we have variations in bulk and trace elements. So something to kind of keep in mind is that some of these are all over the place. Our Hutchinson has positives and negatives. However, our REEs actually concentrate in very similar manners throughout these, which I thought was interesting. So these are averages for all the different salt bodies that we've looked at today. And their patterns, their trends are the same. A lot of this variability is due to dissolution and heat events. They're going to have variations in sources. So that's going to be variations in how much is in there. And then there's variations in freshwater influxes. So the Salina group has had 3 basin flushing events over time. Like we just have freshwater come in, and there's areas where there's no salt located anymore just due to these dissolution events. So we just have a lot of changes going on. So last slide, hard rocks versus evaporates. AREs, American Rare Earths, has the Pelic Creek project area in Wyoming. So it's right here. There's Overton Mountain, and there's, I think, Red Mountain right beside it too, if I remember correctly. There's 2 mountains over there they're targeting. They have an average rare earth oxide grade between 2,300 to 2,900 ppm. And so when we're looking down through individual oxides that they're looking at are in the hundreds of ppm. Averages in these salt bodies are also hundreds of ppm. So rather than stripping, a lot of times we brine these and it's disposed of. We have cuttings, it's disposed of. So this could just potentially, it wouldn't replace, but it could potentially be a new source. So, all right, thank you. I'm done talking. I'm sorry that went a little longer than what I thought. So I have a lot of help on this, but I will gladly take questions and will gladly look for those SEM slides as we're sitting here. So, all right, thanks guys.
Thank you, Julie. Thank you for an awesome talk.
Of course. Do we have, I know I've answered a lot of the questions as we've gone through. So if you guys have more questions. I'm going to look for these SEM pictures.
I would just want to say an amazing talk, and yeah, thanks for handling the questions.
So, well, thanks. Let me see. Some of these might be concentrated on the salt bodies. No, I haven't. So someone asked if I've done hyperspectral imagery of the cores, and I have not. We've done just the XRF and a little bit of XRD and a little bit of SEM. A lot of this is just, we're in the process of publishing a lot of the data just to get out, and a lot of it is preliminary. So one thing I want to do is microprobe, and that can get at, I always get the question is what form they're in. I don't know. I just, with the tools we have right now, I don't know. And so another thing we're going to do is lithium to see how much is in there. So I'm still looking for SEMs. That is salt here. I can show you guys what I'm looking at. So I'm going through. So I think these are the salt. So more of the salt SEMs. Just put it right through. So you can see some of the salt crystals. Let me clean this up. I know not everybody likes Zoom talks, but sometimes it's kind of nice because then you can just dig in your computer and find other things. That is more salt. So that's a clay mineral. See some of the clays coming in. Some of these are a little fuzzy.
I have a question.
Yeah.
What are the main takeaways from the ASEMs? How do they help you in exactly which way they help you identify your work?
So my main thought for the SEM was to see about the salt textures. So coming back through, you can get an idea of primary versus secondary, actually. And I don't get to talk about all the fun things with the Salina one because we just don't have time. And so they have found that if you have like these chevron crystals, it's most likely a primary texture. So it hasn't been redissolved and it hasn't been dissolved and reprecipitated out, versus if you have something like this, where it's almost like it's growing into each other. It's like a mosaic pattern is what they call it. It's been dissolved and reprecipitated out. So the other thing that we need to do is like really correlate what we're seeing in SEM versus the XRF. And so am I getting more REs concentrated in this one versus this one? Is this due to freshwater basin flushing, or was there ions coming in here? And it's not really from the seawater, it's from diagenesis that we're getting any of these concentrations. And I don't have that answer. I need to go, I just need to sit and think about it. Okay, so the missing scandium. I would think, because it's missing in all of them, it's not just like one. It just must not have been present in the seawater. It's either not going to be able to be concentrated and found. So there's a couple. It could just simply be low enough concentrations I can't pick it up. It could be it wasn't there. That's something that is very obvious. So I would actually want to go through and see what's in modern seawater, if there's any scandium in modern seawater. And that can probably tell me a lot about that system. Because some of these have been remobilized and some of them haven't. I actually didn't put the mobilization picture in this section, but that's what I'm thinking. Maybe I wasn't there to start with. That's what because it's not in any of them. Do you think the type of depositional environment of evaporites, the paleo depth of the evaporite for example, can have an impact on the content of trace elements in REEs? Maybe. So like the Luan is deep water deposition. Like deep water deposition versus the Salina group is, I would say in these scores is a little bit more shallow, Sabka to Salina group. And then if we look at, in the interesting part, so the Hutchinson and Salado are kind of almost terrestrial, but the Hutchinson and Salado had the highest concentrations versus the Luan and the Salina, they were not nearly as high. So I'm wondering if it has more to do with location, that kind of paleo depositional environment, like we're able to start transporting it's a closer to the source type thing. So I wonder if they're being sourced from the nearby highlands and everything is coming in from there. So that might be that's a really good insight, is comparing some of these salt bodies for terrestrial versus offshore. So yes, so Don Brown, who is a friend actually, he's asked do you anticipate RE and lithium in the Salina group? And the answer is yes, I do. And so that is our next step, is to send out some samples, because I can't measure lithium using an XRF. It's just too small, it's outside of the range. And lithium in general is kind of hard to do. So we need a lab to do that for us. And I do anticipate finding lithium in the salts, in any of the salts actually. How much, I don't know, but yeah, I think I personally think these could potentially be a very good source. And so Warren, he published like the Evaporite book, right? And I'm sure most of us know that book. And so there's actually an entire section of potential for metals and other elements in these bodies. So, okay. Do I have it? I haven't found the images yet. I'm still looking for them as we're coming through. I'll have to look to see. So John Davies asked, or he asked about the hyperspectral imaging, and then he came back and re-commented on try to get some. It's amazing for seeing changes in concentration. So I'll have to look and see what we can do, because there is a little bit of money floating around from some extra analyses in here. So that might be interesting. Still looking. I'm sorry, I'll find it eventually, but okay. I have a few more minutes. I have class here shortly. You might also look at clastic and algal influxes into modern salt lakes and flats. That would be interesting. There's, I think there's surface precipitations over in West Texas I keep being told about. I need to go check out too. But then some of the other ones, it might require a trip over to Sears Lake. It's not terribly far. I think it's probably a 20-hour drive, but it's closer than some of the other ones of going to the Middle East. So yeah, I think there's a lot of questions, and I think there's still a lot of potential, and there's still a lot of room for research on here. So this is really just a preliminary, this is what we got, we should check it out more type thing. Okay. I need to go get ready for class. So you guys are more than welcome to email me if you have any more questions. I stuck my email in the chat at one point, but I'll stick it in there again. But I do want to thank you guys all for letting me come and talk.
Thanks for joining us, Julie.
So of course, we'll see you guys later.
Thank you everyone for joining.
Yeah, thank you, Julie. We appreciate the talk. Very interesting.
Oh, thanks.